start. Okay, first of all, my sincere apologies. I'm in the middle of home renovations, and it's massively chaotic. But when Joshua asked me, I couldn't say no. So I'm going to talk to you about, I think, a paper most people will already know, but I might just surprise a few people nonetheless. So the Mesozoic terminated in Boreal Spring.
Oh, can you click away the little thing at the bottom there? That's like verbergen.
Sorry, that's
that makes it easier.
I agree. Better?
Thank you. Great.
Right. So the KPG extinction is, as you all know, a sudden catastrophic extinction. I'll talk you a little bit through my methodology, my results, the season of the impact, and the implications of this. So for a very, very long time, the main question has always been, was the end Cretaceous extinction caused by the Deccan Traps volcanism, or was it caused by an impact, or maybe both? Both certainly took place, and it wouldn't even surprise me if both affected different ecosystems differently around the globe. But what you can certainly see is when it comes to dinosaur diversity, like this paper from Chiarenza et al. From 2022, it shows that the dinosaur diversity actually did not decrease despite the volcanism. We can see some marine ecosystems suffering quite a bit through the volcanism, but the dinosaur diversity wasn't really affected until this massive space rock hit Earth. So the KPG extinction, at least for dinosaurs, as we can see it, happened 66 million years ago when an asteroid of roughly 12 kilometers in diameter hit the Gulf of Mexico. It had a 76% extinction rate, and it was a very selective extinction. But when you focus on the effect of this meteorite impact, you actually have two things to consider. One, the asteroid struck and evaporated upon impact. It literally hit the mantle. It caused Earth rock to melt and be ejected into space, which subsequently rained back down on Earth. It also fired a massive shock wave through the crust of the Earth. It also, of course, caused earthquakes through the primary and secondary waves globally, but those waves are quite relevant here. And then lastly, the immense amount of heat that was released from this caused infrared radiation about 1 billion times as strong as the Hiroshima and Nagasaki bombs. In other words, it would have melted the skins off of whatever was exposed to it. But this also means, because of the impact, we can talk about a lost day of the dinosaurs. And so when I was told that there was a site in North Dakota where my supervisor, Jan Smit, had access to, called Tanis, that preserved specimens that died on the day, I couldn't help but be incredibly eager to study it. And thus I was introduced to De Palma and went to Tanis, where I studied this Sites deposit. And this Sites deposit, here indicated in yellow in the bottom left, you can see that it sort of covers a point bar almost like a blanket. A Sites deposit is the effect of these surface waves going through the crust of the Earth, and the crust of the Earth itself doesn't necessarily shake as much, but the overlying water dramatically starts surging forwards and backwards and forwards and backwards. And now in this case of a pool, which is of course very scary for these people, but they were fine. Otherwise I wouldn't have used this footage. This is nothing compared to an asteroid impact. And thus these enormous waves probably reached a height of roughly 30 meters. They mixed materials from the sea, from fresh water, and from land, while tektites, so these parts of molten rock that came from the Gulf of Mexico, rained down from space. So the direct casualties from Tanis were sturgeons and paddlefishes. They were deposited or preserved in the wave direction of the site. So you've got them going forwards, you've got them going backwards, you've got them going forwards again, you've got them going backwards. And on the bottom left, you see an image. There is quite an elevation depth between these fishes. It's not very obvious from this angle, but it was hard to photograph. But you can see the bottom fish. These are two sturgeons. The bottom fish has its snout pointed forwards, and the fish above has its snout pointed backwards. So they were in the ongoing surge or in the recurring surge. Here's another beautiful image of some of these beautiful sturgeons from Tanis. They've got these beautiful ornamented scales, and they're really beautifully preserved. So my research question was, can the fossils from Tanis tell us in which season the meteorite impacted? And for this, I had 1 paddlefish skull, I had 3 paddlefish jaws, and I had 3 sturgeon pectoral fin spines, indicated in pink in the little diagrams here, so you know which bones I'm talking about, because fish have too many bones. So my methods were osteohistology, in other words, looking at the growth marks in the bones, especially here you can already see in this cross-section of the paddlefish jaw, you can really see the growth marks very clearly. I also applied X-ray fluorescence to get an objective of which elements were where. I sampled these growth marks for stable carbon and oxygen isotopic analyses, and I also applied synchrotron tomography. So the growth marks in bones, in these bones, are really similar to tree rings. And that's because these fishes, especially the dermal bone in the dentary and in the pectoral fin spines, they do not remodel as they grow, and these fishes do not stop growing until they die. I mean, they don't grow the same rate their entire lives, but they do not stop growing, which means that they document an annual growth season every year. And you can see a repetition, for instance, in the amount of osteocytes or bone cells. They start to appear early on in the growth season. When they start to eat, you get small, few in between osteocytes. And then as the growth season proceeds into like summer, where they have peak growth, then you get bigger and more osteocyte lacunae. And then when growth slows down, the annulus forms, and then finally in winter, nothing really happens because there's not a lot of food. And then in spring, the line of arrested growth forms, and then they start making new osteocytes again. And you can see this repetition throughout several years, helping us to understand how these bones grew. So the X-ray fluorescence I applied was to record the elements that were present in the bones and the rock, because I needed to assess the degree of diagenetic alteration. I needed to assess, am I going to measure the stable isotope composition of the bones as they were in life, or am I going to measure the stable oxygen and carbon isotope ratios of the rock that was formed after burial? So I wanted to make sure that the isotopic composition was still the original biotic signal. So for the isotopic analyses, I sampled the growth marks with a micromill. So I had to set the trajectories, which you can see here in green. The one in yellow is the active one. I had to reset this about 50,000 times, because after every single increment it did, it would start to deviate. And I would have to calibrate again. They've now since replaced this machine because it's such a nightmare to work with at the VU in Amsterdam. But it was nonetheless quite fun to be drilling out all of these specific growth marks. I applied stable carbon and oxygen isotope analyses, and I'm always just going to assume that people do not know what that is. So when it comes to stable carbon isotope analyses, you've got 2 stable carbon isotopes, carbon-12 and carbon-13, but carbon-12 is a lot more common. You've probably heard of carbon-14. That's an unstable one used for dating quite recent stuff, so it's not used here. But carbon-13 is not preferred by autotrophs. So algae and plants do not like carbon-13. It's too big to make sugar of, so they don't use it to make sugar of. They sort of have to get rid of it. Excuse me. So they use carbon-12 to make sugar, and then the carbon-13 that they take up from the air, they actually preferably put in their extracellular walls in the plants, or maybe the algae like excrete it in calcareous ooze or put it in their exoskeletons, but they don't use it themselves, which means that everything that eats them gets relatively enriched in carbon-13. So the higher up in the food chain you are, the relative more carbon-13 is in your system. But also in the case of feeding seasons, when you eat, you get more carbon-13, and when you don't eat, you get less. So you get this sort of curve in there. Oxygen is a little bit more complicated. You've got 3 stable oxygen isotopes, oxygen 16, 17, and 18. 17 is so rare that it's ignored. like universally, we don't calculate with it because it's barely calculatable or barely detectable. But 16 is the lighter oxygen isotope and 18 is the heavier one, which means that when it comes to evaporation, for instance, 16O will evaporate more easily than 18O. And in rain, it's exactly the opposite. This means that different bodies of water, an ocean, a sea, or a river, have different ratios of oxygen 18. And so that tells you a little bit about whether these fishes could have migrated or whether there was a massive change in precipitation, but not necessarily a seasonal signal. So the synchrotron tomography, I went to the ESRF, the synchrotron in Grenoble in France, at the foot of the Alps. This is actually a picture in the bottom left taken from a forealp. So from the top of a mountain, you can see this enormous ring. I took this partial fish head there, and then they told me, oh, that's nice. Oh, it looks really delicate. Yeah, you have to put it like vertical. And I'm like, what do you mean? And then they said, yeah, you have to put it vertical because otherwise the beam can't go fully through. And I'm like, crap. So that's why you see picture B, which is where I've wrapped it carefully in all the styrofoam I could find and put it vertically in a tube. And on the bottom, you see the experiment setup. Oh, sorry, someone else going to get the door, so that helps me. So you put the tube on a sample stage. On the right side, you've got the shutter where the X-rays come through. And then on the left, you've got the optics, the camera taking the picture. So the specimen rotates, and you take 1,000 pictures of X-ray images of the specimens. So my results. So in my thin sections, I could quite clearly already see the lines of arrested growth. So I could see several years of growth in these fish bones, but this for me was not high resolution enough. It's nice and indicative that they are there. So the X-ray fluorescence, on the left, you see the distribution of calcium, phosphate, and manganese. When it comes to diagenetic elements, you don't expect manganese in the bone matrix. And if you look very carefully, the blue is very present in the vascular canals. So in the center of the bone, you see some vascular canals or in the cracks. And especially on the left-hand side on image C, you see, for instance, that the sediment as well is almost entirely blue, but there's no calcium, there's no potassium leached out of the bone into the sediment or vice versa. So that's a good indicator. Then on the right-hand side of the left image, you see kalium, there's see, I had phosphate on the left, sorry, potassium. Yeah, we say kalium in German and in Dutch, so I'm always messed up with the K. Sorry about that. But you've got silica and you've got iron, same story. We've got iron in the blood vessels and we've got, see, I'm going to do it again. Kalium, yeah, potassium. And silica, you've got that in the sediment surrounding the bones, but you don't have it in the bone matrix, which is comforting because it means nothing leached out or in. And then on the right-hand side, you see an image that has an overview of the calcium. It's a heat map, so it shows you the distribution of calcium. And you can see that, for instance, it didn't really leach out from the outside of the bone. There are some areas that were more delicate than others. These were not sampled. But it does look like, generally speaking, the preservation is good. And then the synchrotron tomography actually confirmed this because on the first scans, when they first started sliding in, I had Dr. Paul Taffero staring over my shoulder and he says, I think you have a brain case. And I'm like, what? And that's what the red arrows are pointing to here. These are the walls of the brain case. It does look like it's been in a car crash because it didn't have a very subtle death, this poor thing. So I am yet unable to fully get this thing out because sometimes the walls are nice and smooth and I can get them out, and sometimes they're all mushed up and almost impossible to segment out. I also found in the scan that a confirmation that these fishes indeed died on the day, because by the time I was doing this investigation, I had already been told to cut open a fish in the field to check for tektites, and I didn't find them, which bugged me. And by now, news has also reached me that some preparators of some of these fishes have complained that they've not found tektites, so they don't see the conformation. I'm not sure if anyone can see the tektites here already, but I will circle them for a minute, and then I will remove the circle so you can see it. Maybe you can see them now. They are these little hollow balls, and the fact that they are hollow confirms that they have been in space, because if something solidifies on Earth, the air bubble will always go to the top and leave, or sit at the top, because we have gravity on Earth. These solidified in space under a vacuum, and so all the air bubbles are in the center, confirming they solidified in space before raining back down on Earth, which, by the way, I think is really cool. And now the paddlefish scanned. I gave it googly eyes so you can see the front. We're going to zoom in and focus a little bit on the gill cover, the nicely preserved one on the other side, which is there. And then I did a higher resolution scan on the gill cover region. So behind the gill cover, you're now going to see the gill arches with the gill rakers. And in between the gill rakers, dead in the center, so not even in the outer gill rakers, but dead in the inner gill rakers, exactly where the stream of inhalation would take place, you can see these beautiful little spherules. So I also focused on reading the growth line. For this, I also used synchrotron scanning. And when you do a lot of synchrotron, when you stack some of these synchrotron slides and you focus on the highest absorption and the lowest absorption, you get figures 2 and 3 in all these images. And in the highest absorption, you get a really clear view of the lines of arrested growth. And when you focus on the lowest absorption, you get a real good indicator of the more abundant osteocytes or bone cells. And in other words, the green arrows are pointing towards summer feeding peaks, and the red arrows are pointing towards winter feeding dips. And of course, these alternate. And you can see that all of these fishes, these 3 here already, they died after winter, but before summer. But that was not enough. I wanted to not just see it, I wanted to have it quantified. And so we segmented out the bone cells. So on the left, you see the synchrotron image in A, and then in B, you see the segmentation of these osteocytes and with a legend of the volume on the right. And you can see these really clear peaks of summer in there. And then when I alternate, or when you look at the graph in C, you can really see this alternation of green, of a peak summer, and then a winter, and then a summer and a winter. I'm not going to repeat all of them. But again, you can see that the amount of bone cells and their volume were increasing after a winter dip, but nowhere near the summer maxima. So when I combine all the data, the stable isotopes on the left, you can see a decrease like I predicted in winter because they're not feeding. And then you see an increase in summer. There is some missing data because not all of my analyses succeeded. But then you see another peak in summer between 1.5 and 1 and 1.5 millimeters. You see a really big peak of summer, a winter dip. Then you see a kind of a poor summer, but still a summer and a winter, and then a really good summer and a winter. And then you see values that really commonly occur between summer and winter again. So we've got stable isotope analyses, carbon in this case, and we've got the osteocyte lacunae volumes, and combined these say this meteorite struck in spring. So with this beautiful reconstruction of Joshua, thanks again for that, we were able to visualize how on a spring day 66 million years ago, the Cretaceous came to an end. But why? Oh, sorry. But that was followed by 30 years of darkness and cold, or the nuclear winter, as we describe it. And although I really, really love this image, I really wonder how many dinosaurs were still there to even experience that, because the infrared radiation probably nuked out a lot of them. And so, but why does the season matter? Well, if it was spring in the northern hemisphere...
Sorry, Melanie. From now you have roughly 5 minutes.
Yeah, I'm going to rush.
Okay.
So from the I'm almost done, actually. So if it was spring on the northern hemisphere, then it was definitely autumn on the southern hemisphere. And of course, the seasonal ranges are quite small, but still, this probably mattered quite a bit because spring is the season of growth. And in autumn, organisms are preparing for winter. So they go into hibernation. And this is not just something like brown bears do nowadays. This is something actually quite a lot of animals do. And there's also different variations of it. You have many animals that are able to go into, for instance, torpor, where they go on sort of standby mode and just make sure that they survive and wait until times improve, which, for instance, crocodilians are very well known for, as well as many other reptiles and birds. So maybe if they were already sheltered, they weren't exposed to the infrared radiation and they had a better chance. And there's other data that actually indicates this because the recovery was over twice as fast in the southern hemisphere compared to the northern hemisphere. So maybe the season had something to do with that. That was my talk. I should stop screen sharing, but oh no.
Oh, it's fine.
I just want to close it. All right.
Thank you very much, Melanie.